This section is on the inverse of a matrix. Now, we've been talking about how you can do arithmetic with matrices the same way you do arithmetic with real numbers. And the inverse of a matrix is analogous to the reciprocal of a number. But only square matrices have inverses. And not all square matrices have them. But we only talk about inverses of a matrix if the matrix is a square matrix. So let's look at this. An n by n matrix A is invertible or non-singular, those two words are interchangeable, if there exists another n by n matrix B such that A times B is equal to the identity. And B is called the inverse of A. And a few facts about the inverse. The inverse of A is denoted by A to the negative 1. Only square matrices have inverses. And if A inverse exists, then you can multiply A inverse times A or A times A inverse in either direction, and you'll get the identity. And this last thing says, a matrix is invertible if and only if its determinant is non-zero. We haven't talked about determinants yet, but I wanted to go ahead and throw that in there because determinants are very important, and there's a good chance if you've done anything with matrices in the past, you've dealt with determinants. And we'll talk about them more later. But let's look at some examples. This first thing says, show that the matrices below are inverses of each other. So what I'm going to do is multiply these matrices out, and we should get, the identity matrix. So let's do this. First up, we'll do 1, 2 times this. So I'm going to get this is equal to, let's see, that's going to be, tell you what, I'm going to write this out. That's going to be negative 2 plus 3. Then we'll get 1 minus 0, 1 minus 1. Then we'll get 3 times negative 2 is negative 6, plus 4 times 3 halves, so plus 6. Then the last one we get 3 times 1 minus 4 times a half. And so sure enough, if you add this up, you get 1, 0, 0, 1. So those two matrices are inverses of each other. You could call this one A and this one A inverse, or reverse vice. You could call the first one A inverse and the second one A. All right. So let's look at using the definition to find the inverse of this matrix here. Now, I'm just doing this for as sort of an example or for illustrative purposes. This is not the best way to do it, but I do want to show you that you can do this. So this matrix, 7, 8, 1, 3. Let's find its inverse. Well, here's what we know. 7, 8, 1, 3. If I take that and multiply it by A, B, C, D, we get the inverse. So basically, I'm setting this matrix right here up to be the inverse. So when I multiply this out, over here, when I multiply this times these and this times these, we're going to get, let's see, 7a plus 8c, and then we'll get 7b plus 8d. And then downstairs we get a plus 3c. And then we get b plus 3d. And that's all equal to the identity. So I've still got this thing here. It's just a 2 by 2 matrix, but each one of the entries is a small equation. And so now I can set this up as a system of linear equations. Basically, I'm going to set this equal to 1, this equal to 0, and so on. Now, you might look at that and say, well, this is 4 equations and 4 variables. But really, notice the A's and C's are over here together, and the B's and D's are over here together. So you could just solve this like two 2x2 systems. So let's see, 7a plus 8c equals 1, a plus 3c equals 0, then 7b plus 8d equals 0, b plus 3d equals 1. And I'm going to solve this using octave. M equals 781,130. Gives me that. That's kind of ugly. All right, so that gives me, let's see, this one was for A. So that's A is 3/13. B is going to be -1 over 13, or no, C is going to be -1 over 13. Then we'll get B and D. Similarly, over here, 780, and then 131. Gives me -8/13 and 7 over 13. So my inverse here, let's see, we didn't have a name for this matrix, so I'm going to go back here and retroactively call it A. Then what we get here is A inverse is, I'm going to factor out the 1/13, write it like this, 3, -8, -1, 7. All right, one more thing. There's a formula that we can use, and we can kind of pull it straight off of here. This formula is for the inverse of a 2x2. If your original matrix is A, B, C, D, then the inverse, if it exists, is 1 over AD minus BC. Now notice what that is. That's the this diagonal product minus that diagonal product. So you can take AD minus BC, then times, I'm going to read this off of the example we did. Here we had 7 and 3. Notice down here we have 3 and 7. So D and A switch places. And what about the other numbers? We had 1 and 8 there. Well, down here we've got -1 and -8. So this is going to be -C and -B. So that's a formula that maybe is worth memorizing for the inverse of a 2x2. And let's see, one other thing, this number right here, AD minus BC, that's the determinant of the matrix. So if that were equal to 0, the inverse wouldn't exist. All right.